And first, I want please to raise your hand if you have heard before about edge computing or edge intelligence. Good. So many people already a bit keen on the topic. For those of you who it's the first time you're hearing about it, I want you to think about maybe 15 years ago, where most of the computing at that time was done on your personal computer at home or at work. Now in 2019, we're very much more into a cloud computing area. You still have a personal computer, I'm sure most of you, but in reality, all the services that you are using are mostly cloud-based. You know, if you think of Gmail, of Dropbox, of Office 365, all of that is in the cloud. And additionally, you have new devices inside your home, such as Amazon Echo or Google Chromecast, which are powered by content and intelligence also from the cloud. And what we're going to discuss today with our expert is that actually we have more and more application where we realize that we need to bring more intelligence directly at the source of the data, which is what we call the edge. So to talk about that, I would first like to welcome on stage Professor Ingmar Posner. He is leading the Applied Artificial Intelligence Lab at Oxford University. He also has co-funding Oxbotica, a leading provider of mobile autonomy software solution.
Hello. Hi. You can hear me. Excellent. First of all, thank you very much for having me. It's a real pleasure to be here. And for the next few minutes, I would like to talk to you about robots thinking fast and slow. Now, AI technology these days is everywhere, right? So we see it in the papers, we have it in our homes, we increasingly see it on the roads. But you might be forgiven for asking the questions, where are the robots? You know, where are those machines that work with us, alongside us? Why can I buy a voice assistant but not a versatile household robot? And robots, of course, operate on the edge, right? Which is interesting for us, particularly in the sense that they need to operate in real time. They act and interact in the world, so they need to make safety-critical decisions. And actually, we would like them to have a knack for creative problem-solving, ideally. All of these things we've traditionally struggled with, right? Now, interesting thing, humans can do it. For decades, AI researchers have sought inspiration in cognitive science, right? And the point that I'd like to make today really is that for the first time ever, we're now in a place where we can actually implement some of these processes and where that conversation might take us, okay? And that's really what this is about. At the heart of this, actually not so much at the heart, but very much a cornerstone of this, together with some other stuff, is machine learning, okay? Unsurprising. And for the purposes of this conversation, I'd like you to think of machine learning as an associative process where essentially we learn a mapping from some input, that doesn't work, from some input to some output, okay? And that mapping could be is-like or is-of-class, and that mapping gets informed by some oracle, which is, you know, effortful, like a human, for example, that provides labels. And this sort of stuff we distill into a machine learning model, okay? Now this we've been able to do for decades, so what's changed? Well, unsurprisingly, the thing that's changed is the deep learning revolution, and deep learning really affords us but exactly two things. The first one is that we can learn some very, very complex mappings now, and the second one is that we can execute those mappings really, really very quickly, okay? And that's going to become useful in just a second. What kind of mappings do I talk about? Well, there's lots of them. Time is short, examples are long. Think about this one, for example, which is sort of out of my, one of my lives, where we say, well, a machine can actually look at a scene and interpret it in such a way that it can predict where a human might drive in that particular scene, okay? Interesting thing about that is that the way we've done this is there's some systems knowledge that underlies the whole thing, so we know where the car is, we know where the car's driving, we know where the wheels touch the ground. We can create training data through systems knowledge, and all of that gets distilled into a machine learning model. Point is, the oracle that informs the model, the oracle whose knowledge gets distilled into the model, is about 100 sort of person years of systems knowledge, okay? And again, you end up with a mapping where you have some input, looks like some output, okay? Another example might be intuitive physics. So we look at this and we go, well, is this stuff going to fall over? Nah, I don't know. Turns out, yes, in this particular case it is, and you might have an opinion when you first see the image. But what you don't do is you don't look at the image, write down the laws of physics, analyze the image, and then roll it forward. When you look at this, you kind of have a gut feeling about it, okay? Interestingly, we can again take all of that to create data, all of that sort of expertise about the laws of physics and the simulator and so on, to distill it into a model, which in this case again is the oracle, which leads us to input image mapped to stable or not outcome, okay? Very, very similar to that sort of notion. Okay, so that's one of many, 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 many examples that we could give you. Where that leads us, though, is sort of this general partition, right? So on one hand, we've got all this knowledge that's distilled into models from different domains. So for example, AlphaGo, like gameplay is a big one. AlphaGo does something very, very similar to that, all the way down to acting, right? And over here, we've got these sort of oracles, like for example, humans, Monte Carlo tree search, systems knowledge, simulation, and so on, right? And you could look at that and go, well, actually, on one hand, we now have this sort of fast notion, and we have this slow notion, right? Very, very cumbersome. Wow, that's very loud rain. Okay. Now for something totally different. Who here knows the answer to this question? Okay, nobody's putting their hand up. I'm assuming you all know the answer to this question, all right? Okay, who here knows the answer to this question? Sorry, the lectern is sort of placed not so great, but, right? Presumably, probably not quite as many, but that's not really the point. The point is that this is very, very typical of these sort of two types of thinking that typically we employ according to cognitive science, right? So on one hand, we say 2 + 2. I've seen this many times before. I don't have to work it out. It's a recall operation, right? So on one hand, we've got to have an intuitive response about what we might want to do. On the other hand, we have the system 2, which you might call reasoning, which basically says, actually, when I see this, I need a pen and a piece of paper or a calculator or a computer or something, okay? And so the system 1, system 2 notion, of course, comes from a place called dual process theory, which was popularized by Daniel Kahneman in his book Thinking Fast and Slow, which presumably some, if not many of you have read. And the notion, again, is that on system 1, you have sort of this intuitive response, intuition, which is very much about being fast, being low effort, being almost involuntary. You can't help but come to some conclusion, right? And on the other hand, you have reasoning, which is slow, which is effortful, which is deliberate, right? And so the question now is there such a thing as dual process theory for robots? And the answer is, well, yes, because I've already shown you that slide, right? It kind of looks like this, where we've got the oracles and we've got the sort of intuitive responses. Now, why is that useful? Okay. Well, first of all, it already buys us one of those things, which is acting in real time, right? So being able to execute those mappings very quickly means our robots can do some stuff, which is great. But then what about the next thing, which is really about knowing when you don't know, safety-critical decision-making, right? So think about those two systems. Think about the intersection of those systems, like the bridge between them, to be a thing called introspection, which is really about asking yourself whether you know when you don't know. And humans have to go through this as well. It turns out, as humans, we suck at knowing when we don't know, okay? But we have a whole bunch of mechanisms that help us make decisions and survive in the world, right? And those are generally known as metacognitive processes, okay? So metacognition is sort of one of three things. It's making a choice, deciding whether you have enough information, knowing when you don't know, and analyzing the outcome. And so it turns out that in your brain there is a process that's known as the feeling of knowing process, okay? Which is the thing that when you read 2+ already decided that this is probably going to be a recall operation and that you probably know the answer, okay? So it's near instantaneous, it's already triggered by parts of a question, and it allows you to select a solution strategy, which is kind of interesting. But of course, being constantly vigilant, constantly going, ooh, I wonder, again is effortful, right? So what if we pull that same trick again about intuition and sort of the oracle and say, well, what if we simply train a system to distill knowledge as to whether you will succeed at a particular task given training data, or given test data, given an input, or how confident you can be in the output. We pull that same trick again. And what you end up with is this notion of performance prediction, which is actually something that increasingly is gaining traction in machine learning, particularly in deployment, okay? So we find it in RL, we find it in robotics deployments, and so on. So that's an interesting thing that kind of pops out of this analogy. Another thing is this notion of learning new skills, okay? So at some point, you did not know how to stack toy blocks. Okay? At some point, probably as a toddler, you went through an exercise like this, maybe minus cat, okay? Where you had some real cognitive strain to build these individual sort of tower blocks, right? And at that point, you were totally in system 2 in the reasoning bit where you really had to think about stuff. What might that look like for a machine? Well, you can imagine that you run an experiment, in this case, for example, in a simulator, where you have different geometries, like this, and you try it in terms of supporting these sort of blue blocks, and depending on the geometry and the pose, this is useful for stacking. It supports the block or it doesn't, right? So spheres are always bad. Blocks, cubes in this sense tend to be quite good. And again, we can take that and we can distill it into this sort of intuitive response of, is a thing stackable or not? And what we end up with is sort of a fairly interesting notion when we take the stackable point and the sort of stability notion that I showed you earlier, and we end up with a way of having a machine build a tower block of things, okay? And the reason why that's interesting is because it's very, very different from how we typically do this. Typically, there'll be all sorts of control laws that we write down, where we reason about the things that are in the world and how we might put them on top of each other, right? And so this sort of intuitive response provides us with a certain way of kind of dealing with this. And where's that going? Well, building tower blocks is one thing. Kind of doing something in the real world is clearly what robots do, but ultimately it goes towards this thing, which you might look at as creative problem solving, right? This notion of you use your faculties, much like this bird does, to open this safe, which is locked with implements that sort of are made for humans, right? The birds develop strategies not just to open this, to manipulate these individual ones, but to open them. And ultimately, that is very much where we want to get to. And where that leads then is sort of two interesting notions that sort of drop out of this analogy, which is why it's important, which is this, that intuition really is recognition. And that creativity is really about association. But at this point, I will have to stop. I'll leave you with this slide. Thank you very much. I hope you had some thoughts.
Thank you, Ingmar. Now the next talk is going to be done by Alex Kendall. He is a co-founder and CTO of Wayve. It's a self-driving car company, which already has some cars on the UK road. So welcome, Alex.
Thank you. So I wonder how many people in the audience have actually been in a self-driving car. Quite a few. So I think they are one of the most underhyped technologies of our generation. They're going to completely change society in so many ways. But unfortunately, the media is, I think, painting an unfair picture of what they can do today. Let me just introduce where we're told they are today. And I want to talk you through maybe a different technical narrative than one you've heard so far, and how we might see self-driving cars become prolific in society in the future. So what have we heard? Well, one of the leading pioneers in deep learning came out and said, back in 2018, Andrew Ng said, hey, they're here, they exist. Similarly, from an industry leader in self-driving, Waymo had a press release in the very recent future saying, actually, they're also here. And our good friend Elon Musk, he claimed in 2015 they'll be here in a couple of years. Well, I don't think many people put their hands up at the start of this talk, so they're still quite clearly not here. And even if we go to 2018, he's still implying that they're going to be here in the future. And now let's look at this quote this year. Unfortunately, this hasn't quite happened. So why is that? Why did you not come here to CogX this morning in a self-driving car cooled very efficiently, safely, and much more sustainably than transport exists today? Well, so this is what self-driving cars looks like today. A car driving on a very quiet, empty road in Phoenix, Arizona. The sun always shines, unlike here, as we've seen today. And, it's a simplistic environment, and this is where they are today, as prototypes, as demos. My question for you, when are we going to see them in a scenario like this? Or let's go one step further. This kind of scenario. This is what we need to build if this technology is really going to be prolific. And this is the kind of problem that we need to solve. But it's a really hard one. You cannot underestimate the difficulty of this problem. It is, perhaps the first time we are giving machines an actual physical interface to interact with the world. And that has big consequences. So what's going on today? Well, at a high level, this is how we're approaching it as an industry. We're trying to take high-definition maps where we tell the car some invisible railway tracks for it to drive throughout the world. We're explaining where things are, where signs and goals and pedestrians and these kind of things we need to interact with are in the world. We add a different sensor for each edge case we encounter. And more importantly, we tell the cars how to drive. We say, under this scenario, you need to do this. And we construct a giant, big state machine that enumerates every kind of scenario that the car could encounter. Now, that might have made sense 10 years ago, and maybe that brute force approach might work in constrained scenarios, but we're starting to see the limits of it today. And you'll hear often people say the edge cases, these scenarios that we can't enumerate an exhaustive list of, that's what's really holding us back today, and that's where this brittle technology is starting to fall down. So let me present you an alternative approach, something different that might be able to move away from this paradigm and give us a technology that can actually learn very complex scenarios at scale. If you look at the numbers too, we're starting to see that they're starting to asymptote at levels that won't even support deployment. So, it's clear that a new method is required, and that's what I'd love you to start thinking about. How can we beat this glass ceiling and get something out there that will scale? So what I've been working on for a number of years, and what our team has spent the best part of a few years putting together, is a new approach based on end-to-end deep learning. One that, instead of hand designing how the cars behave, we rely on the data to learn representations that are high-dimensional, perhaps uninterpretable, but that can fit the complex scenarios of these roads. Now, we've seen end-to-end deep learning completely eclipse any other method in image recognition, speech recognition, game-playing agents. In fact, to the point where you'd probably be laughed at for trying one of these problems without end-to-end deep learning. But not yet robotics. Robotics is yet to go through that revolution, and that's what I think we'll see over the next couple of years. Let me show you one of the first examples of applying end-to-end deep learning and reinforcement learning to a self-driving car. This was a big proof point for us because it showed we could take this technology out of a simulation, out of a video game, and put it on a real car. This is quite a cool demo because it really personifies learning in front of your eyes. This car starts off knowing nothing about the world, and it drives doing completely random actions. And every time it makes a mistake and tries to drive off the road, the safety driver intervenes. And that intervention is what it uses to learn. And you can see after a few pieces of training data, it still can't drive. And so we keep training it a bit more. And now you can see it's learned a policy that is somewhat unstable, swerves back and forth. It'll ultimately crash, but it's getting better. And it's that kind of feedback the car's learning on the, online on the car itself. We haven't told it what physics is, what a road is, and it's learning entirely from scratch in a very efficient way. Now, the exciting thing here is that after that 10 pieces of feedback, the car has now learned how to lane follow. So that was a big proof point for us, but what does that mean for driving? Of course, that's a very small, simplistic, academic example. How can we take that and make it useful society and bring it on public roads? Well, what this means is we can now start to consider systems that were too complex to consider before. We can now learn a mapping that goes directly from sensory inputs and sat-nav navigation data through to controlling the car. And we can learn this mapping very efficiently from data, and that's perhaps analogous to how you might drive. And so this is what we've done. We've produced a system that takes a basic sat-nav app using the phone's GPS, and it's able to take this navigational data and simply see the world around it through its sensors and learn a mapping to be able to control the car. And it does this all online, on the edge, on the robot platform. And so once you've entered in the route, you'll see this car is then able to drive down very narrow British streets. We're no longer talking sunny, wide boulevards of Phoenix, Arizona, but these are quite narrow British streets, tucking in behind cyclists, interacting with traffic. Now, this is the sort of technology that I think will scale. But don't let me kid you, this is a really hard problem, and this car is a little baby. It's only had about 25 hours of training and has a long way to go before it'll be safe enough for you guys to get in it. But it's a start, and I think this kind of method will really give us the capability to be able to interact on these very challenging environments. So how is this possible, and how can we do it now? Well, I want to talk through some of the problems about representation learning here, because what we need to be able to do is extract the state of the world to be able to make these decisions. Now, just a few years ago, this was the core work of my PhD. It was the first time deep learning was applied to this problem of scene understanding or semantic segmentation. And it was pretty exciting at the time. You can see we're able to extract what is in an image and where is it around us from a camera data. But it's still quite noisy. We open sourced the code. A number of self-driving car companies tried to put it on cars, but it was too noisy to be able to drive. Now, what's amazed me is how far this field has been able to come in just a few years. So if we jump forward from 2015 to what our team was able to put together last year, we can now see that a single deep learning model can extract information about the world that is far more rich than just those noisy semantics. We can understand at a much higher accuracy and fidelity than before, not only semantics in the top right, but also the depth and the geometry of the scene in the bottom left, and the motion of how it moves in the bottom right and how the world moves around us. And so once we have that representation of semantics, motion, and geometry, this is why I think we can move away from HD maps, because we can give robots the ability to perceive the world and make decisions and represent the world with a state that they can see themselves. And we're trying to build in this intelligence into the robots rather than trying to bootstrap it through a brute force method. And we can go further than that. Machine learning can also let us leverage simulation. Another thing that surprised me was that we were able to take a car, train it in this cartoon simulator that we built, and put it on the real road with no real-world training data. And this was an exciting demonstration because it shows that simulation can not only be used for validation, but also training. We can get dangerous examples, potentially unlimited training data. And so that's what this approach can allow us to start to think about. So if I was to summarize this method about taking deep learning, taking machine learning, and trying to teach the car how to represent the world and make driving decisions, I think what we're trying to do is introduce this new paradigm that if you compare it to the rule-based approaches, we want to move away from, limited complexity and limited scenarios and move towards more complex domains. The trade-off is that we may lose some interpretability, we may not be able to guarantee performance or have analytical safety proofs, but I think that's a consequence of building intelligent machines. As we move from, human design and constrained settings to big data settings, we really want a system, and this is where we want to move in the top right, is a system that can excel with scale. The more data we get doesn't make the system fall over or become brittle, but what it really does is allows us to excel at scale, to be able to fit data with more and more complexity. And that's what we've seen deep learning do in a number of different data-rich fields. Robotics is coming. We need some more time to build out this technology. And there's, it's not just the case of taking these algorithms from simulation and putting them in the real world. There are new complexities to solve. But that's where we want to move. We want to move to a machine learning-driven, high-dimensional, representation that's learned from data. And that's what I think will be able to cover the edge cases and bring us autonomy. So to conclude, what does that mean for self-driving? Well, it's a complete paradigm shift. It's moving away from large amounts of compute and sensor requirements on the vehicle, but now we want all the compute in the training side of things. It's increasing the intelligence on the car, perhaps reducing the reliance on HD maps and rules that we have to construct for the car to know how to behave. And finally, it's enabling new things like learning from simulation. And really, this is all possible with a very lean and elite engineering team because we let machine learning do the heavy lifting. And this is what I think will bring autonomy for everyone. Thank you.
Thank you, Alex. And so for our final talk before panel discussion, I want to welcome on stage Baguley, who is Vice President and CTO for the EMEA region of VMware, a software virtualization company.
Good afternoon. I don't know whose idea it was to put the lectern in front of the screen, but it certainly wasn't mine. So you've heard an awful lot about image recognition, machine learning, automated cars. Tends to be the main topics when you come to an AI and ML concert. Feels like a concert in here, meeting. However, what I want to do for you today is talk a little bit at a different angle from the enterprise world, from the world where people are building applications today, where those applications are going, and why the edge has been a topic for us CTOs in old world software companies for the last 4 or 5 years. And I've been running projects such as the one we run at VMware called NanoEdge for a while. So when we look at the world today, we've been talking about edge and IoT today and AI and ML, but also you have to bear in mind the emergence of both cloud and mobile. What we're looking at as a society is the rise of 4 major superpowers of technology. Now, a lot of people say, oh, you know, the pace of change is terrible. I don't think we're ever going to keep up. There's so much tech going on. It's all happening so fast. None of these are happening fast. Cloud's been happening for the last 10 or 15 years, depending on how you look at it. Mobile's been around for at least 10 years if you talk about the iPhone being the start of smartphones, but a lot longer than that, depending on how you look at it. AI, it's a 50-year overnight sensation. Okay, I've been doing AI. I was being taught AI at university. And edge and IoT have been around for at least 5 years as a leading topic. The interesting thing is that they're all happening together at the same time. And the important thing about human invention and innovation is it actually comes when people take existing technologies and put them together in a way that no one thought of before. So the innovation that we see in our industry isn't necessarily people inventing new things. Self-driving cars is people taking existing camera technology, compute technology, and cars and putting them together in a way that no one's thought of before. And when you look at it, there's about 6 or 7 different viewpoints about what sensors you should be using, what algorithms you should be using, whether you should be using HD maps or not, all these different things as people explore how these things intersect. So a lot of the conversations I'm having with people at the moment, particularly CIOs and CEOs of large corporations as they look forward to their next 5, 10 years, is how are these intersections going to affect them? And specifically how, for example, AI and edge are going to intersect, and that's what I want to talk about today. What we're looking at realistically is an evolution of the famous statement of the 90s from Sun that the network is a computer, or the computer is a network. We're now where the world is the application is a network. We have to not look at any individual component in isolation. We have to look at the self-driving car in the context of where that data goes, where it sits on the back end, who's talking with it, who's interacting with it, because the person who gets in the car is going to probably have a mobile phone that wants to interact with that. There's a whole bunch of stuff where it's not all just about one thing in one place. And I'll give you some really detailed examples in a second of where we're seeing applications that have exploded, as was said at the start, out of the data center. But really it comes from a misconception. The misconception is that in our world of IT, we re-platform things. And that's what we've trained ourselves to do. Everyone talks about this age, that age, whatever. What we did was we started with the mainframe. That's when we first played with computers. Then along came mini computers, Unix, AIX, HPUX, RS6000. So what we did was we re-platformed from the mainframe to Unix. Remember that? That was the big trend. We did re-platforming from mainframe to Unix. Late 80s, early 90s, that's what we did. Unless you're a government, in which case just leave it on the mainframe. Then, in the 90s, we re-platformed everything from Unix over the next 15 years to x86 platforms. Unless you're a government, in which case you left it on the mainframe. And then, what we did in the last part, the first part of this century, was we took all our x86 workloads and virtualized them. And that was really the next step. But all of that is re-platforming. Take this, move it somewhere else. Take this, move it somewhere else. So then along comes someone with cloud, and they go, oh, so obviously we've got to re-platform everything onto the cloud, have we? My answer is no. That's not what's happening. What's happening is those applications now are exploding, both horizontally and vertically. The other thing I always get asked when I'm up on stage talking about applications is, but Joe, surely it's all about serverless and PaaS, and isn't that the trendy thing we're meant to be talking about? Why are you talking about infrastructure and edge and AI when everyone's putting everything on serverless and PaaS in the real world of application development? My answer to that is, it's one of the answers. And this is where chromatography comes in. Now, hopefully, some of you will remember back in your days at chemistry lessons, that day where you got out the special paper and you got the little liquid and you dropped it on, and over the next however many minutes, it spread out into all these beautiful different colors as it exploded into the different elements and components that make up that particular liquid, that particular mixture. Well, that's exactly what's happening with our applications. Those little dots down there are the things that are sat on mainframes and on x86 servers right now. That's DB2 and WebSphere and WebLogic and all those old Java apps. And what's happening is we're not just re-platforming them. What we're doing is we're helping them explode. And in 2 axes. The first axis is we're actually saying, well, what we're going to do is no one of these is an answer. So in the world of compute, we really have three answers that are the cloud answer, apparently. Infrastructure as a service, which is where you rent a whole virtual machine. Platform as a service, where you rent kind of parts of a virtual machine because you turn it with an app, and the platform works it out. And then SaaS, which you all know, because that's Office 365, etc. And so what's happening is no one of these is the answer to all our old apps. What you're finding as you go forward is you need some things are solved by this one, some things are solved by this one, some things are solved by that one. And of course, because we work in the IT industry, we didn't want to leave it being that simple. We thought we'd add another couple of layers just to make it a bit more confusing. So recently you've now got containers as a service. Some of you may have heard of the rise of Docker and Kubernetes, etc. So that's all in that space. And then FAS, which is functions as a service, or serverless, so that's all the Lambda functions, all the other things you have to think about. And then, of course, just to make it a bit more complicated, it's not just about which one of these we choose, it's whether they're on-premises or off-premises for most enterprises. So now I've got 10 boxes to think about, and that's my application landscape. So where the hell does Edge come into this, Joe, and why are you telling us about all this application stuff? The reason I'm telling you is because Edge is just part of the future application landscape. But it is a key part that has to be included in everyone's thinking around application development as we go forward. Here's an example for you. I have a large German car manufacturer. Be interesting if I can still say that in 10 years. And what they're doing is they are running in their factory functions as a service. So on premises, they have little gateways that sit on every pole in the factory, and they're tracking what's going on in the factory, where the cars are, how many tires I've got left, all that kind of thing. They're writing that down to an on-premises SQL Server database, which is infrastructure as a service. Then they've got something funky written in containers that extracts from that and puts it out here to Amazon S3, where they then have platform as a service running on Google, which then provides a live real-time dashboard to their management of what's going on in the factory. But then they've got third-party suppliers that can come in and connect into this S3 database now and see the state of the factory stock levels so they can predictively ship. And there you have a modern app. Sounds scary to most normal people, but that's normal for an application developer today. It's not just in one place. So what you're seeing is as applications become more complicated, as infrastructure becomes more spread out, as the components of solving that business problem that you're solving with an application increases, automation no longer becomes an optimization you do to something that you manage. It becomes a design requirement. And so now what you're seeing in the industry at large is a research drive around AI and machine learning specifically for the management of large, complex computer systems. So those people that are turning up to use AI and ML on huge clouds, we're going to have to use AI and ML to manage those in the first place. So why is Edge important in this story? What's Edge got to do with all of this? Well, the reason why you're hearing Edge now is because of the stuff you've just heard about. Networks are not fast enough or wide enough to keep up with the amount of data that is required to do the execution at the edge. If you think about it, do you seriously think that that Renault Twizy could live stream all of that video information to some cloud somewhere else, even over 5G, and get an adequate response time? Short answer is no. I mean, the best way I use to explain this is I have home automation. I've got Google, and I've got Hue lighting, so I can sit in my kitchen and I can go, hey, Google, turn off the kitchen lights. And lo and behold, 5 or 6 seconds after it's done all the communication up to the cloud, worked out what I've said, come back again, found my Hue hub and turned my lights off, lights go off. Winning, right? Because it's still quicker than it takes me to get off my arse and turn the light off. So that's why people do it. I also am an early adopter in AI and machine learning because I drive a Tesla, okay? And the Tesla has autopilot in it. And in that, I've got a setting on how far it keeps me from the car in front whilst it's doing lane keeping. And the numbers go from 1 to 7. And that I've found out in the UK is the number of Audis that you can fit into that gap. And so you've got to think to yourself in the scenarios you're talking about, when that car pulls in front of me, do I want to wait 6 seconds whilst the car talks to the cloud? No. So that's why what we're looking at now is a resurgence of edge computing. As things come out of data centers, as I've got people trying to do real-time video analysis of people walking around their stores to track what they're looking at and what they're shopping for, I need more and more compute at the edge than ever before. And as we'll talk about later in the panel, hopefully, we're going to see more and more of that in telco networks to support 5G, pretty much everywhere you go. So as we go forward, the edge is not just one part, it's pretty much the leading part of future application technologies. Thank you.
Thank you.
We need mics.
So we have 22 minutes of panel discussion, and then our speakers are going to stay around so that if you have questions, you can come and talk to them directly. So the first thing I want, just I hope an easy question for a panelist, which is, what does edge intelligence mean to you? You've already given some example during your presentation, but if you can give additional one to give us a better picture. Who wants to start?
I think I just did. For me, very much it's about, as an application developer, looking at how I can take advantage of compute storage at the edge. If you look at it specifically in the terms of Tesla, in the context of what was just been talked about by my other two panelists here, the machine learning doesn't happen in the car. The machine learning happens back in the cloud. All you've got in the car is an execution engine for an AI model. And so, as we go forward, it's interesting to see how the shift may happen as more processing power is available at the edge, that we start to get the cars probably learning for themselves at the edge, as opposed to all the learning happening in the middle, then periodic pushes and updates of an AI model for them to execute. But certainly, when I'm getting to the point where we've got huge amounts of processing now being put into cars alone, it starts to open up massive possibilities. But thinking wider than that, I'm talking a lot more about telcos, because as telcos start to realize they can push more and more compute closer and closer and closer to you, the subscriber, it starts to mean that every cell tower itself will be a point of execution of code and a point of storage. And when you start to look at the entire cell network as a huge meshed computer, the possibilities of what you can then deliver to end users are huge. So actually the excitement there is what we can do for the gaming industry around workload placement, all this other kind of stuff. So you can have real-time streaming, VR, Fortnite on your 5G mobile phone. So there's a whole bunch going on.
I personally think we're seeing a trend away from sending all of our data through to the cloud and doing the intelligence there, through to now taking a representation on the edge on the device and then sending that through to the cloud for decision making. And in the near future, we'll end up in a paradigm where it's all of the intelligence and decision making is on the edge, and giving those devices, those robots, the intelligence to be able to make these decisions, I think requires us to give them more trust. And to use Ingmar's framework, I think if we can reduce the amount of times we have to dip into that oracle, to that offline, slow thinking that can train and correct our system. But if we can provide more intelligence and more trust to the actual device to make its own decisions, I think that's going to give us more reliability and safety.
Yeah, I mean, generally I agree with most of it. For me, the whole operation on the edge is really about operating successfully, and I don't think it has to be one or the other. I think extremes are bad. It doesn't have to mean that all the intelligence is in the actual device. It doesn't mean that all the intelligence sits in the cloud. Ultimately, I can cross a road pretty safely, but every now and then I need to look at a book or Wikipedia, depending on where you're from. And so for me, it's very much about that trade-off and the mechanisms that actually trigger the fact that I know that I now need to look something up, right? So for me, the intricacies are not so much in whether it's in one place or the other, but actually how the symbiosis is managed, and that for me is important.
So, you've just mentioned, right, that we're bringing more computing to the edge, and you've mentioned about the representation that's going to be built at the edge and then sent to the cloud. How much do you think of the learning is going to start happening onto the edge? And, if that happens, how do you share the knowledge acquired by all the edges?
Okay, me. Wow. Okay, so for the past decade or so, I mean, I started out my career very much sort of in machine learning, mobile autonomy. I spent a lot of time in sort of autonomous cars and so on. And very early on, I kind of came to the thing that I thought was kind of the core question, which brings me back to the knowing when you don't know. Okay, so in the context of this, I can learn online very nicely, but typically what we find is that some of the information that we add online is kind of not quite right? And if you do that a lot, what you get is something like, for example, semantic drift in semantic segmentation, that what you assume is supervisory information is sort of increasingly off, okay? Which brings me back to knowing when you don't know. So for me, that question is very, very central to being able to actually improve intelligence at the edge. So a lot of it revolves around that.
So the demo I showed of the Twizy learning to lane follow was entirely learned on the edge on the robot itself. To do that at scale, so the demo I showed you of it driving on Cambridge streets, that entirely had to be offline on computers. And I think the kind of intelligence we're building these days is very much, let's train it for 6 months in the cloud on large compute servers, and then let's put it on the edge. I can imagine a future very soon where we are able to actually learn online on the device. And I think that has a number of benefits. You can personalize services, you can personalize robots, you can personalize interactions to what they're doing. You can deal with domain shift if things change in the context of driving, if the culture we have around driving and interacting changes when we roll out autonomous vehicles. Then if we can learn online, then we can potentially adapt to that more quickly. But I think I think this is somewhere, some direction we'll move. I think the key is that we need to have an understanding about how that adaptation can happen, how efficient it is, and how reliable it is.
Yeah, I think we're a couple of ways away in a couple of areas. So autonomous driving, I always challenge Elon Musk that I'll happily accept that we've got full autonomous driving when the car can drive towing a boat down a single track country lane in Devon, where it then meets someone else towing a caravan. If we can deal with that, then I'm kind of happy. That's, like your picture. But more widely than that, what we're looking at is a rise in the computative possibilities at the edge in terms of low power and high processing. So there's a lot of research work being done by the friends at ARM, for example. And so, we've actually brought out a hypervisor for ARM for the first time as people are looking to do that. And I'm starting to say, okay, fine, well, we're starting to democratize technology now. So if I've got the ability to build a cluster, I'm not kidding, I can build a 3-node cluster from some Raspberry Pis with some pretty reasonable processing in it and some storage for $150. If I start to put those places as data gathering engines, not necessarily learning engines, but data gathering engines that can then feed into more generalized central machine learning engine, what we're simply doing is increasing the amount of data. So I think the great advance that we'll make over the next 5 years, I suppose, will be the amount of data we can gather to punch through these ML for regressive deep learning or whatever it is. That's really where we need one of the challenges I talk to any autonomous driving company is the amount of data, and Tesla rave about how much data they've got compared to everyone else, but that really does give them an edge. The other question I ask, actually, I'll be interested to, I'm not a professor of AI, but it's quite nice to be on stage with one. Do you not think there's some secret artificial intelligence algorithm that we've not found yet? And all we're doing right now is making horses go faster. And in fact, because we've got so much compute and so much data, we can now finally say, yes, great, we can get this to work. Is there some secret trick we're missing that's 100 times faster? Do you think there's something in there, or is modeling the human brain to do these things the right way to do it? I shouldn't be asking questions as the panelist, but sorry.
No. It's a discussion, right? You should.
Okay, so that's a small question. Is there a secret algorithm that we haven't found? That the answer is I don't know, because we obviously. If I knew, that would be great. Do I think there's actually? I think it's increasingly about the mechanisms that we use and how these things interplay. Right? So we can say, well, we have a neural network the size of the brain, fine. Our systems don't do all the things the body does, right? So my car doesn't have a heart and so on in terms of body function, right? So it's not clear how much of our brain capacity is actually used for all of this, right? Now, an interesting thing that is absolutely open in machine learning, and I think that's one of the biggest questions right now, is this relationship between what we call model complexity to task complexity. So, for example, in the olden days, I could say, well, if in school you sat in your math class or in your geometry class and it said, fit a line to these data points. Do you remember this? right? And then sometimes you kind of got data points that weren't actually aligned, they were from an ellipse, and clearly the line was the wrong model, right? We kind of have the same problem now, because ultimately deep learning, which many people talk about, of course, is it's function approximation, right? So that's your line fitting. It's just that deep learning can fit some pretty complex sort of functions, which is great, really, really good. Now here's a question. What's the capacity of a particular network? We don't really have an answer to that, which seems odd, right? And even more perplexing, if I say, you know what, I would like to come up with a very simple task, which is I would like to find all pedestrians in a bunch of images, please. I can't tell you how complex, like mathematically complex that problem is, right? So I can't actually tell you what size of network or what set of function I need to be able to solve that particular problem. And it's some fairly fundamental questions like this that will help us understand the question that you ask. And this is also some of the most exciting bits, right?
I'd go even further and say I could believe a world where the latest and greatest deep learning model we have today could be good enough in terms of model capacity for a human-level self-driving car system. You know, the 200-layer convolutional net that can map 1 million dimensions from a megapixel image down to, say, 2 outputs, steering and acceleration. That kind of model, we're not anywhere close to hitting the capacities for this model. What's really key is that all data is not created equal. In self-driving, you typically collect 1 terabyte of data an hour on a car, and it's understanding how to actually train these models and build that representation is that's the key here. And these whether just expanding these models is the way to do it, that's a completely open question. But the capacity of them is very hard to reach.
What's intrigued me when we're going through some of this machine learning model play is that if you remove human bias from systems, suddenly they surprise you. And I'm sure you've found that. I've found that we're looking at using machine learning for managing large compute systems. I talk about huge, multi-thousand node cloud systems and applications that spread across huge environments globally. And we found one that had suddenly improved the performance of a particular element by 67%, when we have a team that works on performance tuning that was on marginal gains of 1 or 2%. And we thought we'd tune as much as we could out of that system. And suddenly this thing jumped to the 67% performance improvement, and we were confused as to why. It was doing something in the system that no one would have ever thought of. It was actually, if you really want to know, it was changing the frame length of network packets dynamically, which was just freaky because we had software-defined networking. No one would have thought of that, but because it saw it do it, because, I'll try that works, and it iterates down that hole. So I'm really intrigued when we look at some of the potentials of the models that you're talking about, the non-human bias iteration and what it may discover. Is there anything, in those areas? That's kind of cool for me too.
Yeah, I would just go back. I would like to go back a bit more to the edge discussion, but I'll give you that, and then you can answer the next question for me, which we've touched, on some advantages that doing the computing at the edge gives. So, like, you can't send a full video stream to the cloud. You can give meaningful representation. You can also adapt it, personalize it. What other advantage can be bring up by doing more computing to the edge?
Okay. All right. So just very briefly back to the bit about the capacity. So typically, what we do is we over-specify our models massively. We know that generally. We don't quite know what the right capacity is, but we pay a price for that, right? And the price is execution speed still, right? So bigger network takes longer to run. Takes more space in terms of storage, takes more training data, and takes more energy. All of these things are linked, right? So answering the question of how big does my model actually need to be is a pretty substantive part of this endeavor, okay? That's just sort of my 2 cents to that. I'm trying desperately to remember your question. Oh, how much compute should be on the edge?
No, it's what are the advantages?
Okay.
The one we've already mentioned.
Independence. Independence is good, particularly when you have limited bandwidth, and that could be because the technology isn't there for the amount of data that you want, or space, right? So if it takes you 7 minutes to hear back whether your rover did what you needed to do, you would like it to be intelligent enough to not fall in the ditch, right? So it's that sort of trade-off that we're talking about.
And there's also interesting things to be said about the human bias, but I think I probably have to hand this over now.
So it's interesting you mentioned space. Thinking more, when I say space to me, I don't think about Brian Cox's space, I think about disk space. I'm an infrastructure guy. And one of the big things for us is the ability to discard data at the edge. So take inference and get rid of stuff before it comes back. You talked about earlier, coming back with an inferred data set that's a subset of the larger data set that you get, because literally the amount of data we're going to be collecting, you don't want to keep it all. There's not going to be a reason to keep it all. I mean, you can literally throw it away and take the bits that you need out of it. Now, the more that I can put more intelligence at the edge in edge devices, the more that I can start to discard data at the edge. Actually, that's one thing we're looking at under SDG 9, under the sustainability goals around infrastructure, is how can we optimize to make sure that we're not unnecessarily sending data across networks and thereby wasting energy. So how can I define more efficient systems and use artificial intelligence to optimize the efficiency of these applications? Because we've built a rather wasteful ethos in application development. You have unlimited, you can build your models. I don't know how big it is, but let's just go for times 10 and we'll see what happens. It's this ability to say, okay, fine, as we go forward in application development, how can I make sure that we're optimizing for the most energy efficient application? And I think the application of AI and machine learning technologies at the edge with computing that's low power computing, we can really make a massive difference to the energy consumption of some of our most important applications as we go forward. And importantly, these are architectural decisions we should be making today before it's too late and we end up with the Bitcoin problem with regards to energy, for example. So we need to think about that too.
The last thing I'd add is that by working on the edge, you reduce the barrier to entry and reduce the systems engineering complexity. I think this is very important because you don't have to rely on large service providers, on network infrastructure, communications, and it really does become, at the extreme, a Raspberry Pi, an actuator, and a sensor. And I think that is incredibly important for getting this technology accessible to society, and it just also reduces the capital cost of entry and the effort required to put these systems together. Because, I mean, Occam's razor, simplicity can often be the best solution. So reducing engineering complexity, I think, is another key benefit.
Okay, so you've mentioned maybe like 2 big models which are not utilized as they should be, and that's consuming a lot of energy, and that's already a topic that you mentioned. So what do you think are the main paths forward to fix that, to make edge computing and intelligence fit into more, the power that you can get from a car or from smaller edge application? What are the main paths? Is it computing? Is it smaller model? Is it?
Computing's not the issue today. I think we have more than enough compute on our robots to run these things. It's entirely in learning. How can we build a robust representation? How can we learn something that's sensible and safe? I can give you so many anecdotes about systems we tried to learn. The lane following one I showed, for example, we trained that car to drive as far as it can without the safety driver taking over, which the safety driver took over if it left the lane. Now, the first thing the car learned to do was it would zigzag down the lane because it drives further if it does this. These models cheat. They try and find the best statistical correlation in the data. You can think of other examples, like a car would learn to stop at a traffic light because it's close to other cars, not because the color is red, but there's a better pattern in the data that's more dominant with a higher signal-to-noise ratio if the cars are there in front of you, as opposed to having open space, which suggests that you can drive. And so these kind of the limitation is entirely in how can we train and learn better representations in decision making. I'm of the opinion that compute is ahead of the game, and we're yet to catch up in terms of intelligence.
I don't really have much to add to that. I think that's pretty much right. Yeah.
On the compute piece, we're at a kind of it's an interesting juncture right now. As there's this decision point from an energy and an efficiency and a compute perspective as to whether it's better to go with a universal processor that's low energy and work out and do everything in software on top of that, or whether it's better to drive down task-specific processors, GraphCore and others. So will we end up with ultimately very specific individual task-specific processors, not just FPGAs, but much, much deeper than that? Or are we going to go with some kind of universal model such as an ARM processor or some other RISC-based platform and do everything in software on top of that? And from a cost perspective, from a development perspective, are we going to get returns on one or the other, and what works better as a longer-term model? And we don't have an answer for that. So, to your point, I think that's one of the big gambles or bets for the next sort of 4 or 5 years is which way we're going to go down with those particular pieces. You've got people like Tesla now making their own specific chip as they branched off from NVIDIA selling general purpose AI chips, other companies coming up with specific AI chips, and then other people arguing, no, I can do it all in x86 and it's brilliant or whatever. I think it's an interesting space to see as that fleshes itself out.
Okay, we have 3 minutes left, and I think a lot of people must be hungry by now. So, or 1 minute maybe. One last question: do you think that deep learning is going to be the core of edge computing, or not?
Yes.
For the foreseeable future, yes.
Yeah, I qualify it with for the foreseeable future maybe, but there's nothing privileged about deep learning.
Okay, so I think I want to thank you, the 3 speakers, for your presentation.